Okay, so good afternoon, everyone. Let's get started with our class. So till now, we have been looking at different versions of the common source amplifier, and in the process of looking at the different versions, or rather the different loads, we understood a lot about how the different ways of connecting transistors work, right? So how does diode connecting work and things like that. So we've looked at a lot of concepts. We've also looked at how to evaluate their noise performance, their bandwidth, frequency response. We looked at the signal swing limits, right? And we've also looked at the transfer characteristics. And basically, through all these exercises, we get an understanding of how circuits behave and also how you design circuits and how you analyze circuits. Okay. So now let's move to the common gate, common drain, and cascade amplifiers. So let's start with a common gate amplifier. Now this is very simple, similar to in the BJT based design. You would have a common base amplifier, right? So it's very similar to that. So how do you construct this amplifier? Basically, you have a MOSFET, right? And let's say you have a certain load RD. This is VDD. Now this is given some bias voltage, right? And the input is given to the source. Okay. So basically, you can just give the input here. All right. In other words, you can basically say that the input itself has got a Vin and there is a, or rather let's call it as Vs and Rs, and so this is the way that you actually give your input. So we started off with just a terminal which we called as the input, and now what we have done is we have modeled the source as the voltage source with a source resistance. So this is pretty straightforward. So it doesn't matter which type of stage is there before this common gate, right? Whether it's an actual sensor that you're trying to amplify or some kind of a there is another stage of amplification before this. Whatever it be, you can always express it as a Thevenin equivalent circuit. Now there is a problem here in the sense that the drain current, right? So ID is made up of IDC plus IAC, right? Now the small signal current is of course flowing through the source, right? But where will the DC current flow? All right. So in some cases, let's say this particular source that we call, this can either be a sensor, or it can also be a previous stage of amplification. In fact, many times it can be another transmitter. I will show you why we give this thing. So whatever it is, many times you may not have the luxury of having the source absorb all your DC current. Okay, so your DC current is a good thing not to have DC flowing through this one. Okay, so in order to fix that issue, what can we do? We can just basically put a current source here. Okay, so this current source is basically going to bias your, or rather let me just call it as IDC. Okay, and you can probably have a capacitor. Now this capacitor is basically optional, okay, because a note about this capacitor, if cap size is required is small, or cap is external. Okay, so for example, if you are talking about audio frequency signals or some kilohertz, tens of kilohertz range signal, you cannot put a DC block capacitor on chip. Why? Because then you will have an entire chip just made out of capacitors, right? The density of capacitors is very small, very less on a chip, and therefore if you want some 1 microfarad capacitance, you cannot implement it on a chip. It's not possible. Okay, typical values of capacitance, see, using MIM and MOM, it is typically limited to maybe few picofarads at the maximum, okay, or typically less than 1 picofarad is what is used. And for other requirements where you need higher capacitances, probably tens of picofarad can be realized using MOS capacitance. And MOS capacitance is a nonlinear capacitance, and usually it is used between the a node and a ground. Okay, so because of all these factors, you cannot put large capacitors on chip, and therefore either it must be external to the chip, or you should be at a very high frequency where the value of capacitance that is required drops down to the order of few picofarads or even lesser. All right, so basically only then, otherwise you design it in such a way that the current source takes all your current, and then you have only your signal current coming in. So this is a very interesting circuit. So we want to know basically how this particular circuit starts working. Okay, so let's first do what we call as the transfer characteristics or the large signal characteristics. Right. So what is the transfer characteristics? Basically, we have V in at the input, we have V out in the y-axis, right? And the circuit is this. Let's just simplify. We have RD, you have VDD, and you have this MOSFET, right? So this is some VB, some bias designed in such a way that you take this. Let's say you have a, or in other words, let's instead of having this, let's just say we are directly giving the input. All right. So in this case, when your Vn is 0, what can you expect? You can unmute and answer. So in this case, when Vn is here, Vn is 0 or close to 0, what is the output voltage? So the output is taken from the drain, right? So what will be the output voltage?
Zero.
Okay, so it will not be 0, but you're kind of close. Okay, it will not be 0 because this transistor. So right now, when Vn is 0, this transistor is seeing a full gate to source voltage of Vb. Okay, and what is happening is all the current is flowing through Rd. So VDD minus that IDRD is this V out, but this V out will not go down to 0 because there is current flow here. Okay, and because of the current flow, right? So what happens is because of the current flow, this will most likely be in the triode region, right? It has a very large gate to source voltage and very less drain to source voltage. This will be in the triode region. So because it's in the triode region and current flow is there, it will not be 0. It will be a little above 0. Okay, so something like this is what will happen. Now as Vn starts increasing, what happens? As Vn increases, the VGS of the transistor decreases. Okay, so this results in ID decreasing. Okay, if ID decreases, Vout will increase. If Vout increases, VDS of the transistor will also slowly increase. Okay, because when Vn linearly increases, ID decreases non-linearly, right? There is, if you take a square law model, it decreases by the square of it, right? And therefore, the slope of VDS, VDS and VGS will decrease, or rather VGS will decrease linearly, whereas VDS will increase non-linearly. Okay, so basically you will have some kind of behavior like this. So here the transistor is in, this is the triode region. Okay, so here it is in the saturation region. Okay, beyond a certain point, right? And then what happens beyond a point, as you keep increasing Vin, what will happen? just imagine if you keep increasing V in, yeah, someone told something, I couldn't hear.
The VGS will fall below threshold voltage.
Exactly. So VGS is fall below, and somebody said like it will get into the cutoff region. Exactly. So exactly where will it go? That is basically when it reaches VB minus VTH, right? It basically goes into the cutoff region, and here once it gets cut off, you'll basically have VDD, right? There is no current flow. V out becomes VDD. Okay. So this is how it basically works. All right. Okay. Now let us look at the small signal equivalent circuit. All right. So let me draw this here. Okay. So so even if you assume that there is a this thing, so even if you say okay, we'll just take this arrangement. Now even if you assume a current source and capacitor DC block capacitor to be present, now anyway when you do a small signal equivalent circuit, that goes out of the picture. Okay. So let's start with the device, right? So this is the gate, this is the drain, and this is the source. So drain to source you have GM VGS. Okay. And you also have what? Because this bulk is connected to ground, you will have GMB VB, yes. Okay. And then what else will you have? You have R naught. So these are the three things which are between the drain node and the source node. This is the gate node. What happens to the gate? Gate is connected to a DC bias, which means it is AC ground, right? Now what happens to the source? Let's say this is RS, this is RD, and this is VS. Okay. So this is connected to RS and VS, right? And what happens at the output? So this is your output node. You have RD going to ground directly, not to source. Okay. So this is our small signal equivalent circuit. Okay. Now let us try to write the expressions and see what will be the gain. Okay. Now what is V out? V out is nothing but, let's this node as Vs. Okay. The voltage at this node is Vs. Okay. And so let's write the equations. Okay. So what is the thing? It is minus GM plus GMB VBS plus V out minus Vs times V by R divided by R naught. Okay. So all these three currents are being drawn out. This into RD is your out. Okay. This is your V out. Now we need to figure out what is VGS. Right. So what is VGS? VGS is like this, and bulk is also connected to ground. So VBS is like this, right? So this is your bulk node. So what can we say? VGS is equal to VBS equal to minus of VS. Correct. So now you can substitute this, and then you can solve for this equation, right? And so you can go through this derivation. So I don't want to spend the time doing all the derivations. Okay. So what you will find out is basically that okay, you basically recognize that VGS is equal to VBS is equal to minus VS. And what is VS? VS is nothing but this entire current that is flowing here, right? So let's say this is the current that is flowing. So the same current has to come through this. Okay. So if you call this as, let's say, I1, the same I1 is flowing through RS. Okay. So you just realize that, and then you say VS is nothing. VS. Okay. Oh, I'm confusing with two VS here. Let me just rename this as V in then. Okay. So if this is V in, so Vs can also be written as what? V in minus this entire I1 times Rs. Okay. So you substitute and then do some algebraic manipulation. You basically get V out by V in this case being equal to Gm plus Gmb times R naught plus 1, okay, divided by R naught plus Gm plus Gmb into R naught times Rs plus Rs plus Rd. Okay, so this is the exact expression that you would get. All right, and this expression will help us to understand what is going to be your uh, gain that you will get. Okay, so you will notice that the gain is basically positive. All right, so that is one major difference that you will have. All right, so the gain, the point that we need to look at, gain is positive, which basically means that the output and input are in phase. All right, and the other thing is you will also see some similarity between this expression and the expression that you will derive for common source with source degeneration. All right, okay, so it is more like, you know, the Gm R naught plus 1 times Rd divided by the kind of expression that you have common source with source degeneration resistor. All right, okay. So now the other thing that we can take a look at is the gain is fairly good. So if Rs, the other point that we need to consider is if Rs is very low. Okay, so if it's a fairly good sensor, or if the previous stage has, you know, is a good voltage amplifier, the internal resistance is lower. So if Rs is low, right, so then what happens is the gain expression tends towards a common source expression. All right, so the gain will be more. So if Rs becomes very low, then basically you get you know, you will basically ignore Rs, and if R naught is also fairly high, and if R naught is very high, okay, basically your gain will reduce to something of the form of Gm plus Gmb times Rd. All right, so this is how it will resemble. So of course the gain is being reduced by the presence of an R naught which is not very high, and also the presence of Rs which is not very which is not low. Okay, all right. So now another thing that we are interested in fact this is the thing that sets apart a common gate amplifier, is the input resistance. In fact, like those who took the RFIC course in the previous semester will remember that we used a common gate amplifier as an LNA, right? Because we saw that the input impedance is something lower, and I think many of you had designed, at least we went through those equations and how to design it and so on, right? So now let us look at, so right now we are looking at the low frequency response. Okay, so there in the RFIC course we looked at a common gate LNA where you are looking at input frequency which is in the order of 1 gigahertz or, you know, thereabouts. Now we are looking at signals which are much lower, okay, less than 1 megahertz kind of signals. Okay, all right. So now let us look at the input resistance. So you can basically redraw the same expression, right? And you can look at the input impedance. So how do you do the, sorry, you can redraw the same small signal equivalent circuit, and then you can say that, you know, the gate is grounded, and then you have you know, GM VGS, you have GMB VBS, and then you have R naught. Okay, and so this is your RD. Okay, and basically what we are doing now is we are removing the source and we are connecting a test voltage source here. Let's call it VT, and what we are interested is to find out what is IT. Correct. So if we find VT IT, we will be able to figure out what is your input impedance. Okay, so now the first thing that we realize is the current that is flowing out, this IT is the same current that is flowing here. Correct. And so therefore you can basically write this expression that what is VT. VT is what? Basically, it is IT times RD, right? This voltage plus the voltage which is flowing. I mean, if the current is flowing like this, the voltage across R naught. Okay. So what is the voltage across R naught? It's basically R naught times the current that is flowing through R naught. What is the current flowing through R naught? We can say it is IT minus GM VGS minus GM VBS, right? And now we know that VGS and VBS are equal to, V minus of VT, because this is your gate to source voltage, and another point, oops, yeah, another point, this is B, this is VBS. So we can say that VGS is equal to VBS is equal to minus VT. So now you combine all these things and you write VT by IT. The expression ends up being something like RD plus R naught divided by 1 plus GM plus GMB times R naught. Okay. So now if you look at the input impedance, you can see that RD plays a role in the input impedance. Correct? The input impedance depends on the output impedance or the resistance at the output. Okay. So RD is coming into the input impedance picture. Now this situation is remedied. Okay. So we can kind of write it as RD divided by 1 plus GM plus GMB times R naught plus 1 divided by approximately you can write, I mean, it is R naught divided by 1 plus GM plus GMB times R naught. Now we know that GM into R naught is the intrinsic gain, right? So it is supposed to be fairly larger. So you can kind of approximate it and say, okay, this is RD divided by GM plus GMB times R naught plus 1 divided by GM plus GMB. Okay. So now if RD is small, what happens? If RD is really small, then the second term dominates, okay, and the input impedance is more close to, okay, if RD is tending to 0, Rn will be approximately equal to 1 by GM plus GMB, okay, and this also happens when R naught is really large. You kind of end up with the similar expression, all right. But if RD is very large, and R naught is smaller, okay, then what happens is the input impedance starts increasing, okay. So in fact, like as we saw in the RFIC course, and for those who did not take it, when you have a receiver, okay, a wireless receiver or even a wireline receiver where you have 50 ohm transmission lines on a PCB, okay, for example, let's say your DDR RAM or something like that, okay, you have high speed connectivity between the different IC on a board, right? When you have very high frequency signals passing there, you use a 50 ohm transmission line, okay, and we all know from our microwave theory that the input impedance should be equal to the transmission line's characteristic impedance, or rather the load impedance should be equal to the characteristic impedance of the transmission line. Only then you will not have reflection, only then you will have maximum power transfer, right? So for those applications you need to have an input impedance which is kind of equal to your characteristic impedance, okay. So for many of our RF systems, the characteristic impedance is nominally taken to be as 50 ohms, okay. So if you want an input impedance of 50 ohm, you cannot get it out of a common source amplifier directly. It is not possible because at lower frequency, the common source amplifier's input impedance is only a capacitive impedance, right? And therefore, if you use a common gate, here your input impedance, and you make sure that your R naught is larger, right? You can improve your R naught by putting a cascode, okay? And you make sure that RD is not coming into the picture. Then what happens is you can design, okay? It is possible to design Rin in the range of, let's say, 50 ohm or in the range of 75 ohm. Okay, 75 ohms is for cable television at here. Like if you look at your old television sets, it will be written as antenna with 75 ohm, right? So that's the characteristic impedance for television which was there, and also for all other RF systems is a 50 ohm, and therefore the input impedance is very conveniently low, right? So if you just increase the GM and the GMB, right, you will be able to achieve the input impedance that you require. All right. So for example, if GMB is not there, that is you use a triple well. See, suppose you want to get rid of this GMB, what can you do? You basically have to get rid of your body effect. And in order to get rid of your body effect, you have to tie the bulb to the source. Correct? How will you tie the bulb to a source? See, this is intrinsically tying B and S is intrinsically possible in PMOS. Okay, because everything comes with its own N well. For NMOS, you have to use what we call as a triple well transistor. I have discussed this earlier. That is, you put a well within a well, right? And you have a triple well transistor where you can connect your bulb to the source. Okay, so if you do that, your input impedance becomes almost equal to 1 by GM. So for 50 ohm input impedance, you will need a GM of 20 millisiemens. Okay, so with that you can design for your common gate amplifier. All right. So any doubts, any questions? Okay. So here again the output impedance is yeah. So let's also look at the output impedance, right? So the output impedance is what? Of course, you can do an elaborate this thing, right? So what happens is when you are doing output impedance calculation, you set the input to 0. So basically what it becomes is just RS to ground, and you have RD here, right? And this is also AC ground, right? This is an AC ground, right? So if you look at the input impedance, the output impedance, right? So you, when looking up, you see R up is basically RD, and looking down, what will be the impedance? Can you tell me? What will be the impedance?
R naught plus RS.
Is it just R naught plus RS? We have derived this, right, in the case of cascode current mirror or current sources. It becomes R naught plus RS plus GM R naught times RS. Okay, so it's not only just the sum of these two impedances, it is this impedance getting magnified by the intrinsic gain of the transistor which is sitting there. All right. So this is the, so now what happens to your R out? R out basically becomes RD in parallel with R naught plus RS plus GM R naught RS. All right. Okay. So you see that the takeaway point here is that, so always remember cascode. If you have a cascode, or if you have, like, even for the common source with source degeneration, we looked at it, right? Like if you have in the previous class, right? So the common source degeneration is also something similar, right? You have a transistor with an impedance at the bottom. I think we looked at it yesterday. I'm not sure, right? So this is the impedance of a cascode. All right. So the takeaway point is R out depends on RS, or in other words, the output impedance is also dependent on the source impedance, and the input impedance is dependent on the output impedance, or the RD or RL, whatever you have. Okay. So this happens because the R naught is not very high, and there is this kind of a bidirectional thing that happens. Okay. All right. Now let's move on to common drain amplifier. So we can again talk about the noise performance. We can talk about the bandwidth. So when you talk about bandwidth, what happens? You have 1 by R out into CL, right? So if you have some load capacitance here, the bandwidth becomes 1 by 2 pi R out CL. So this might be mostly the dominant pole, right? So let's say this is the pole 1. Pole 2 can also be, let's say there is some capacitance at this node, right? So it becomes 1 by 2 pi Rs times, okay, Rs parallel to Rn times the C in, that is here. Okay, so that you, of course you can derive that expression. Okay, all right. So common drain amplifier. So this again is something that you would have studied, right? So basically what happens, you give the input at the gate and you take the output at the source. All right. So what is the point of a common drain? I think all of you would have studied. This is very similar to a common collector amplifier, right? And this another name for this is emitter follower in a BJT. So here it is called as a source follower. Okay. So if you look at just the, let's forget about the, let's say we have some, you know, right. Let's just forget about the load and all that. Okay. So now what will you say, how does V out DC compare with V in DC? What is V out DC when compared to V in DC? How is the difference? Just look at the DC. Don't look at the small signal now. Just if you think about only DC.
Sir, if VDC is very low, then it will be in the cutoff region. So V out will be low. And if VDC is high, then
Okay.
it will be like a short circuit. So output will be high.
Why short circuit? I didn't understand.
Not short circuit, like it will be in the saturation.
Okay, it will leave the saturation, go to triode. Okay, okay. Now I'm just telling you that we assume that M1, let's call this as M1. M1 is in saturation. Okay. Under this condition, what will be the relationship? V out DC can be written as what? V in DC minus this VGS here. Correct. All right. So in other words, let's say you have a, let's say this is V in DC and you have some this thing. Let's say VGS is this much. Okay. So let's say V in DC is 0.8 volt and you have a VGS of let's say 0.4 volt. Okay. Now what happens? Your V out DC will be at 0.4 volt. Correct. Now, if you have some kind of a signal which is coming here, okay, so I think all of you are familiar with the emitter follower or source follower. You know that the gain is less than 1. Okay, it can never become more than 1. It will only be lesser than 1. And you try to keep it as close to 1 as possible, right? Now, what happens? The gain basically is almost 1. Only thing is the DC is level shifted. Okay, so this is what is called as level shifting. This is analog level shifting. Okay, you have an input which is coming in at, let's say, 0.8 volt. Okay, you want to just shift the DC level. Okay, what you do is you put a common drain. Okay, so the gain is almost close to 1, and what you do is the DC voltage alone has shifted. So this is also very commonly used in the industry for many applications where you need to just shift the DC level down or up. An NMOS transistor obviously will shift it down. If you use a PMOS transistor, yeah, someone had a question.
So, sir, it behaves like a clamper.
Uh, clampers, okay. Yeah, you kind of shift the level, that is true. Yeah, you can think of it if you want. But typically what happens is you don't get the luxury of putting capacitors on chip. All right. So for clampers, you need capacitors, right? So what happens is the on a chip, especially for lower frequencies, let's say you are building an audio chip, okay, or you are doing something where it's the baseband of a transceiver or something which is like, let's say, less than 100 megahertz kind of number, 5 megahertz, 10 megahertz is the maximum signal that you are dealing with. So the capacitors, DC block capacitors that you need to put becomes extremely large. Okay, you typically need some nanofarads or microfarads type, depending on the frequency range at which you are working, and that is not possible to be implemented on chip. So when you want to shift the DC levels like this, this is the technique that is often used. Okay, so if you want to shift it down, you use an NMOS. Okay. Conversely, if you want to shift it up, you use a PMOS. Okay. So how will a PMOS be? Basically, you can, put a current source, right? And you have the input. This can be grounded, right? This is your V out, right? So this is your I naught. This is to basically bias the transistor. So V in, and then you have a certain VSG, or sorry, VSG. Okay. So this output will be at a higher potential. So in one of the lab assignments, I have asked a question like that, where you have to design a level shifter basically, where you shift it by a certain amount, and you have a certain bandwidth constraint and things like that. All right. So you have that. I said I'll upload it yesterday, but I could not finish it. So I'm about to finish it. So I'll just send it. So I will upload 2 files, one for hand calculation submission and another for lab. For the MTech students, you need to submit the lab. You have to do all the lab assignments, okay, and you need to submit it separately. For the BTech students, of course, BTech and MTech students and PhD students will have to work out the written assignments, basically where you have to calculate certain things and things like that, and pick any. I have given 4 lab questions. Okay, you can pick any 2 and work it out. So that is sufficient for the BTech students. The MTech students have to do all the 4. Okay, so anyway, it's a good design exercise. I know it's quite a bit of work, and for analog design, let me tell you, it doesn't come very easily at the beginning. So many things you will think that you understand in class, but then when you start actually playing with the transistors in simulation, you end up realizing that things don't work as you plan it to be, and so there is that learning curve which is there. So I'm telling you upfront, but these exercises, lab exercises that I'm giving you, will give you the exposure that you need to learn to design circuits. Okay, so that learning curve will be there, but so please spend some time. Don't take these assignments one day before the submission deadline and try to see what you need to do. And also what I'm planning to do is these assignments that you submit, a part of that will be, the 50 marks for the internals, okay, some part of it will be taken from these assignments. Okay, so your project will probably contribute to around 30% of your final credit, 30 to 35%. 15% will come from these assignments. Okay, all right. So we will so keep that in mind, and so do it sincerely. Start from day 1, because you will have some learning curve in the process. Okay, all right. So now so one of the use cases for a common drain amplifier is to be used as a level shifter. All right, but it also has a very important use. So let's think about it. Now before we go there, let's look at the voltage transfer characteristics. Okay, so let's consider a NMOS for now. Okay, so let's say this is V in, and let's say you have a certain current source. Let's say this is fixed at I0. Okay. Now what we are interested in, as we have been seeing all along, is if you have V in on the x-axis and V out at the y-axis, right? So if you are going to ramp up V in, let's say this is how V in is going to go linearly, right? This is with the slope of 1. How will V out change? Can you tell me? Can you guess it? So the key to this is, of course, let's start with the easier portion, which is basically when it is in the triode region. Okay. So here, when let's say this is somewhere here, okay, there is a fixed current which is flowing, I0. Okay. So since it is a fixed current which is flowing here, right? The VGS is also fixed, right? It has a certain W by L ratio, and in order to support this current I0, it requires a certain VGS. Okay. And because the current is constant for all values of Vn, VGS is constant for all values of Vn. Okay. So that is the important part that you need to remember, okay, or appreciate or kind of understand, that VGS is constant for all values of Vn greater than threshold voltage, since I0 is constant. If you change I0, it will change. So then where is the rest of the voltage going? The rest of the voltage is going to be across the current source. Okay. So V out is going to be exactly equal to V in minus VGS. So this whole thing starts working only after the threshold voltage. So if this is your threshold voltage, till then, okay, the whole thing is at 0. Then what happens? You kind of have a parallel line, and there is a constant difference between these two, and the difference is nothing but the VGS. Okay. All right. So your gate voltage is going up, your source voltage is also going up. That is why it is called as a source follower. Okay. The source is following the input. All right. So this is our source follower. Now let's draw the small signal equivalent circuit. Now the small signal equivalent circuit, let's say, let me draw this. So what we are really looking for is basically, so what happens is, sometimes you can, this, before we go into the small signal equivalent circuit, this can be implemented in various ways. Okay. So it can be implemented as a very simple way to implement is to put a source resistor and take the output. Okay. So this is your V in, and as we saw in last class, for a common source with a source follower, right? What is the difference between common source with a source degeneration and this particular circuit? Basically, there you took the output at the drain, right? And you had a drain resistor, right? And you took the output at the drain. So here you are taking the output at the source, and it becomes a source follower. All right. So here what happens is, basically, of course, what we talked about, VGS is fairly constant. Okay. As V in increases, we looked at that negative feedback action. We said that this particular structure will keep ID fairly constant, right? And therefore V out follows V in. Okay. Another way to implement it is basically to say that, okay, I know that I need a current source here, and so let me design a current source. How will I put a current source? By biasing this transistor in saturation. So this is in saturation, this is also in saturation. You take the output like this. All right. So how will you generate VB? This is generated using current mirrors. Okay. So using a current mirror, you can generate a source. So in your assignment, lab assignment also, you can either use a resistor or you can use a current source. Of course, I have given a question where you will need to use a PMOS input device, okay, where you need to have a level shift. up. Okay, level shift up. All right. So by using this, you can basically bias this, and of course, any real current source will have a current source and a shunt resistance. The same is the case for this. Okay, and all the things that we looked at earlier, right? Like you can have a single transistor current source. You can also have a cascade current source if you want. Okay, so all that works well. All that you are doing is you have a current source. We did all this discussion saying current source, current source, current source. That can be implemented by using either a single transistor current mirror or a cascade current mirror. So same thing goes for even the common drain amplifier, where we talked about current source biasing it, right? Over here, I think I drew a current source. So this also can be implemented as a transistor which is operating in saturation. We have already looked at current sources and current mirrors, so you can implement it in any way that you want. Okay, depending on the requirement of the shunt resistance, you can do it. Okay, so now let's draw this source follower small signal equivalent circuit. So this is the gate. So the gate is given to the input, and this is the drain. So in this case, what is happening to the drain, right? So I am basically taking this particular topology. Okay, so even if you use a current source, it will have a shunt impedance, and when you do the small signal equivalent circuit, you set the current DC current sources to 0, which means it's an open circuit, and only the shunt resistance comes, so it is equivalent to the same circuit. Okay, so here the drain is connected to VDD, so which means it's an AC ground. We have GM times VGS. Again, you will also have GMB times VBS, and yeah, you also will have R0. So let's ground this. We have RS, okay, and Vin is defined between this and ground. VGS is defined, this is, let's say, VS, and VGS is this, okay, and also VBS, let's say the body is connected here, and so VBS is like this. Okay, so we have already done something very similar for the common source with source degeneration. So you can write the equations and you can look at the gain. Okay, and the gain value, I'll just give you the final answer. This is fairly straightforward. We have already looked at the methodology. So it becomes GM times RS divided by 1 plus GM plus GMB times RS. Okay, so this is the gain that we will get out of this, and you can see that this is definitely less than 1, and you can make it as close as possible to 1. Okay, and this is what you need to do. Okay, and what about the input impedance? Input impedance, basically, let me use a different color. You can basically set a input impedance is very high, right? It is just an open circuit. If you are not considering the capacitances, it's basically an open circuit. What we are interested in is basically, this is V out, so you don't need to say it is Vs, this is V out. So in order to do the output impedance, you connect a test voltage source, measure the current which is going in, right? And you can do Vt by It, and you will see that R out, okay, is equal to 1 by Gm plus GMB approximately. Okay, if you neglect R0. Okay, so what we are seeing here is common drain amplifier. Okay, the input impedance is very high, but then the output impedance is very low. Okay, so this you can think of as something like a unity gain buffer. So this is your output impedance. Let's say this is Vin, and the input impedance is very high, and this is almost equal to 1 into Vn. Okay, or let's say some factor, this factor AV times Vn, where AV is very close to 1. So this becomes a very good voltage buffer. What is a voltage buffer? See, suppose you have some source, right, and you have a very high source resistance. if you have to drive a load resistance, what happens? If Rs is high, V out is a fraction of, let's say, Vn. Okay, but if you want to drive this load impedance, but without having this large voltage division that is happening here, what you can do, basically you take this Vs, this is Rs, you put it through a common drain, right, and you put it through a common drain, what happens? Now your output V out, okay, will follow the output input, but then you are having a very good, you are not having such a bad voltage division. Okay, the voltage gain is almost close to unity. Okay, only thing is you have to make sure that this RL. So if possible, the best thing would be to put a capacitor, but many times it is not possible, and so you should be able to design it such that it is able to do. Okay, you design the current source such that it is able to handle it. Okay. Now the other thing that we see here is, if you have okay, we have not yet looked at OTAs, but suppose you take a common source amplifier, for example, right, and now RD, if you connect it to this RL directly, what will happen? The gain drops down to GM-RD parallel to RL. If RL is lower than RD, okay, your gain will just go on collapsing, or you have to compensate for it by increasing your GM, okay, which means you burn a lot of power, which is not at all a very good option. So what do? You have a common drain amplifier as your output stage. Okay, so let's say you have a common source amplifier, okay, something like this. This is your Vin. So this is your CS amplifier. Now you give this to a common drain amplifier, right? So let's say you have a current source here, or let me implement the current source. This is VB. Now this is going to drive this RL. This is your V out. Okay, so this is a common source, this is a common drain. So whenever you need to drive a resistive load, okay, you have to use an output stage, and one of the most commonly used output stages is basically a common drain stage. Okay, only when you need even larger power, you go for class AB amplifiers or class B push-pull amplifiers and so on. But if just not too much current is required, you use a common drain stage. So the common drain has got two major functions. One is to act as a voltage buffer, and the other is to act as a level shifter. Okay, all right. So this is very routinely used, especially when you have an op-amp. All right, this we'll be doing in the next few classes. Right, once you start designing OTAs, the output impedance of the OTA is very high. The output impedance of your operational transconductance amplifier is very high. So you have your OTA, and then you have your common drain stage, and now this whole thing together becomes your op-amp. All right. Now let's also talk about bandwidth. Okay, bandwidth we know is, let's say, when are we concerned about bandwidth? That is, if you have, let's say, this is your current source, you have some let's not talk about the load impedance. Let's just say there is a CL here. Okay. Now what is the bandwidth here? Bandwidth here is nothing but 1 by 2 pi R out into CL. Now we know that for a common drain amplifier, the R out is very, very small, right? The R out is in the order of 1 by GM plus GMB. Okay, that's the input impedance of a common gate amplifier, right? If you remember the discussion that we had just some time back, for a common gate amplifier, we saw that Rin is equal to what? 1 plus GM plus GMB, and we said that you can make it such that you can design amplifiers which are having input impedance of 50 ohm, 75 ohm, 100 ohm, things like that. Okay, so now you are seeing the same impedance, but that is the output impedance of your common drain stage, right? So I said that you are having the same expression here, 1 by GM plus GMB. Okay, so now what happens is the bandwidth very high compared to let's say CS or CG amplifiers. Okay, all right. So maybe with this I will conclude today's class, and tomorrow I'll just do the cascodes and then move over to differential amplifier. Basically, we'll just touch differential amplifier and directly get into OTA design. Okay. So when we get to OTA design, you will appreciate all what we have done so far. You can you will see that all these concepts that we have learned so far comes in very handy there, and then we will quickly move through the op-amp design. Okay. So any doubts or any questions? Okay, so we'll conclude the class today. So this assignment that I am giving today, it will be due in 2 weeks time. Okay, so please make sure that you are finishing it and submitting. All right, and if there is, I've seen that the group has come to up to group number 9. I am yet to see if all of you have uh, enrolled in some group or the other. So if you have not, please form group number 10. If you already, all of you are enrolled, then it is fine. Pick your topics and please put it in the group. Okay, so just put your group number and the topic that you have chosen. Okay, all right. So thanks everyone. Have a nice day.